All right, let's go ahead and get started. Hi, everyone. My name is Elena Harkness. I'm the Executive Director of Current. We are Chicago's Water Innovation Hub, and I'm really excited to be here today for our third Innovator Showcase Series event. This one on the hot topic of removing PFAS and other emerging contaminants from drinking water and the environment. So as always with our Innovator Showcase Series, these are really fast pitch events designed to give several emerging innovators a chance to share the technology they're developing to solve a specific water-related problem. And with me today, I'm really excited to be sharing this presentation floor with our partners, ChicagoNEXT, and a new partner, Halo. So I'll be introducing our partners in just one moment. Before we get started, just a couple of housekeeping items. We do have quite a lot of people online today. This will be recorded. Please mute your lines. We'll be taking chat questions in the chat bar, so please go ahead and submit your questions there. We may not get to everybody's questions during the short Q&A. These are about 5-minute presentations with 5 minutes of Q&A after, but also the innovators are free to join in and try to answer questions in the chat bar, so we'll try to keep that really dynamic and interactive. So thanks again for joining us. We'll have you wrapped up in an hour here. Real quick run of show. We've got 4 innovators today that are going to be presenting their work. In addition to those 4, we'll have a very short time for Q&A at the end and a couple of wrap up and next steps. So we're looking forward to hearing from Cyclopure, SolvePFAS, Hydrus Technology, and Zyvant. Great. So a couple words on Current. Current is Chicago's Water Innovation Hub, or Chicago's Water Cluster. We're a startup founded in 2016, and our job in brief is to try to strengthen the connections between the demand side for water innovation, the utilities and end users and industry partners that all have an interest in growing the pool of innovative technologies to solve water challenges, and the supply side. So it's the entrepreneurs, innovators, and researchers that are coming up with novel solutions to meet the water challenges that the world has. Part of the way that Current works, part of the way Current works is by hosting events like this, where we're just trying to really bring together folks on both the supply and demand side, ensure that we've got investors, universities, industries, utility partners, all in the room and on the line, and also just increasing public education about important topics in water. We also work by bringing pilots into the real world, helping to bring technology into demonstration sites and overcome some of the commercialization challenges it faces in going to scale. Next, I'm going to turn it over to Eben Kyriakos, who is the head of ChicagoNEXT, one of our key partners in this initiative. Eben?
Thank you, Elena, and I want to thank Erin for this wonderful opportunity to join you guys today for the Innovator Showcase Series. Again, my name is Eben Kyriakos, Director of ChicagoNEXT at World Business Chicago. World Business Chicago is the city's economic development organization chaired by Mayor Lightfoot, our dedicated initiative to drive inclusive growth across the city. And ChicagoNEXT is WBC's initiative to really support the tech economy and the growth of our innovation ecosystem. And we do this work with a cross-section of leadership representing large corporates, medium-sized technology companies, startups, great innovation hubs and organizations like Currents to bring everyone together to make sure we're going in the same direction when it comes to promoting Chicago as a global city for technology, innovation, and entrepreneurship. The 2 things I do want to highlight here is kind of our current initiatives to support the tech economy during COVID. One is Think Chicago, which is connecting university students with tech companies that are hiring. And this is really to support the students who are trying to navigate a really difficult job environment, but also support companies, especially since on-campus recruitment has been severely limited. And then the second piece is Chicago Venture Summit. We were supposed to host this in 2020. We officially announced that we're moving it to 2021, which is the city's flagship VC conference, one of the largest venture events in the Midwest. But right now we're currently working on a soon-to-be-announced startup growth program to support venture-ready Chicago startups who want to connect with active investors and also corporate partners. For more information, I'll make sure to share our LinkedIn info on our chat. And again, I want to thank Current for this wonderful opportunity to join.
Yeah, it's great to have you. And obviously, World Business Chicago, a founding partner of Current, and ChicagoNEXT, a critical partner in all that we do together. So thanks so much for being here. And now I want to introduce Kevin Leland from Halo, who is a new partner of Current, and really excited. Kevin comes out of Chicago's technology innovation ecosystem, in Northwestern. And Kevin, over to you to share your solution.
Great. Thank you so much, Elena. We are really excited to be partnering with Current Water and to help commercialize more solutions to water-related challenges like PFAS. For those of you who aren't familiar, Halo is an open innovation network that connects scientists and startups directly with R&D-driven companies for research collaborations. And we do that through a simple RFP process. Companies post a research challenge or interest, and we source solutions and proposals through our global network of scientists. We work with some of the largest companies in the world, including Baxter, which is obviously right in our backyard, as well as private companies like Georgia Pacific. And what makes Halo really different is we take a network approach to collaboration. As many of you know, research is often too early when it's first identified by a commercial partner. But on Halo, we help build these relationships today. So when that technology is mature enough, you already have that connection. And that obviously more closely simulates how things work in the real world. We have several focus areas in applied research, one of which is water and wastewater. So we've already built a really robust network in that ecosystem, and we're excited to build upon that in partnering with Current Water. And Elena will be talking more about what that means exactly at the end of the presentation.
Great. Thanks so much, Kevin. No, we're really excited about this, and it's obviously solving one of the kind of critical connection points between the supply-demand side for water innovation. So really excited to have you. And now I'm going to go ahead and launch us into our first innovator. I've got Frank Cassou from Cyclopure ready to talk to us about the novel technology they're working on. Frank, over to you. And make sure you're unmuted.
There we go.
Yeah.
Thanks, Elena. Appreciate it. Appreciate ChicagoNEXT and Current and Halo for organizing this program. Really great resources for tech companies. I came out of Silicon Valley in the late 80s, and it's really great to see this in the Chicago area. You're going to get our experts on Thursday to talk in kind of more detail about engineering, but I'm going to give you a little bit of background on the company and our technology in my short talk here. So if we could move to the next slide. Maybe just, okay. Everybody loves a label, so you know, our tag is just if you want to kind of compartmentalize Cyclopure, we're a clean tech company. We are developing novel materials to remove trace contaminants from water resources. So that's just our tag. We have locations, operations here in Skokie, Illinois. This is where our research and development activity occurs, and then we have corporate offices in San Diego. They get the sunshine. So, next slide. So the heading here is, you know, it really tells a lot about, you know, Cyclopure and what our market opportunity is. You know, we're targeting a niche application, removal of trace contaminants from water supplies. While it's niche, the market is huge because of the obviously water resources to supply populations. And obviously it's of great social importance, both from a health standpoint and a cost standpoint, because a lot of, as a result of micropollutants being pervasive in drinking water supplies, folks have turned to alternative sources like drinking water from plastic single-use bottled water, which is, you know, not only bad for the environment, but it's also very expensive. We formed Cyclopure, my co-founder Will Dicktail, I know he's out there somewhere in the digital world, to commercialize a really cool technology that he developed at the Dicktail lab to using cyclodextrins, which are derived from cornstarch, to remove trace contaminants. And I'll go into the technology a little bit more in a second. But really a driving factor in developing a water treatment technology is that it's affordable. It has to be cost effective in order for it to translate into a consumer-friendly cost. You can't have an expensive technology that doesn't transfer to the to households. So we, you know, our focus is to solve this problem as a polishing step in water treatment and to be part of the solution to enable consumers to use their tap water at home in a affordable and safe way. So that's the big mouthful of the picture of the company. Next slide, please. George? No, okay. So how do we do it? We do it, as I mentioned, with cyclodextrins. Will's technology was quite innovative. Cyclodextrins are a natural absorbent derived from corn, but in their native form, they're soluble, so they haven't been able to be used in water treatments previously. So Will devised a nice innovation to cross-link the materials in a way to make them non-soluble and to be available for use in drinking water treatments. Now, what's really special about them is that they are these tiny cups. You can see them here. The diameter across the cup opening is 0.78 nanometers. So ideally suited to small trace contaminants, and you know, incredibly, in a gram of our materials, there's 300 quintillion cups at work seeking out trace contaminants. So it's an efficient process, single step, and it's also one that we can tune to various contaminant groups. So that's how we do it. There's a little diagram over here as we start to corn and come all the way around to our cups.
Frank, I just have to say, I don't normally break in, but the diagram here, it's like the positive looking coronavirus. It's like the thing, like the crown. It's nice to see something positive with a crown of, yeah.
Okay, yeah, very good.
Great to see that.
Speaking of coronavirus, my hair is still in phase 2. But anyway, we'll go on to the next slide. So we have, over the last couple of years, adapted Will's technology to develop two materials, two absorbent materials that are used in removal of micropollutants. One we call Dexorb, which is tuned to pharmaceuticals and pesticides, and the other one, which people are probably interested here, is Dexorb Plus, which is tuned to PFAS compounds. We call it Dexorb Plus because we've added a positive charge to the compound that makes it very effective against PFAS compounds. Just a note up there, you can see what micropollutants are. Why are they important to pull out of water? Because they can cause health risks at small part per trillion exposures. And what's a part per trillion is 1 drop in the Lincoln Memorial reflecting pool. So really tiny stuff. And current technologies of coagulation, flocculation, and separation, they do a great job, but they miss the tiny stuff. So why is Dexorb an ideal technology? I see I'm running hard here on the time, but it provides selective absorption through 2 mechanisms, hydrophobic and electrostatic, which actually is kind of the nature of PFAS. They have both a hydrophobic tail and electrostatic head. So this makes uptake and removal quite rapid. We have size exclusion because the cups are 0.78 nanometers, so that screens out all the background constituents and very high capacity. You'll hear more about that on Thursday. And eventually these all translate into treatment benefits of effectiveness against long and short chain PFAS. We perform equally in all water matrices, so groundwater, surface water, wastewater, and leachate. And then another value add is ability to regenerate and desorb easily. Okay, let's move on. Coming to the end. We adapt the material to multiple form factors, loaded filter papers, granules, extruded blocks, so we can use it in multiple applications. We're producing it here in Skokie at 60 kilograms a month. Let's move on to the next slide. And so that allows us to bring the materials to market in multiple channels. First to market, we're already there with analytical applications. We have a passive sampling home water test kit that's available that we launched in 2019. We are developing here in the lab filter cartridges for residential use. These will be gravity pitchers and under-the-counter products that are a combination of loaded filter papers, loose media, and extruded blocks. And then our longer term piece is going to be municipal treatments, drinking water treatments, wastewater. And we have pilots ongoing in the US and Europe. Okay, next slide. Okay, so this is the teaser. One of the things our material enables is moving to smaller footprints. So you can think about it going from mainframes, large stationary tanks, to desktop portable tanks. This is kind of a teaser, just like hovering over a Netflix program. This is what Dr. Yuhan Ling will talk about on Thursday, kind of some of our treatment applications. So anyway, I've gone over a little bit, sorry. that's a wrap, Elena.
Not a problem. That was fantastic. I know we've got a couple of questions coming. I see Mark Bartler in the audience asking, is the tech meant to be applied as a point of use or point of entry solution, or at the municipal level? Like, what's the...
If you hop back, George, to the prior slide, just real quick, that's probably a better place to talk.
Yeah.
We use it in residential, point of use and point of entry. So things like under the counter and whole home. And then we also use it in municipal applications, drinking water treatment, wastewater polishing. And so you'll get more of that on Thursday. That's a teaser to come in and do, but the material is really flexible in its use. So we're happy to bring it to homes in a lot of ways, consumer direct, and then also through municipalities.
But not industrial, correct? Just municipal and residential.
No, it could be. It definitely could be industrial. Although, you know, we see the need and the demand more in residential and municipal.
Yeah, okay. And then we've got a question from Sue Hendrickson, disposal of sheets or residue?
Disposal of sheets or residue, that's a good question, Susan. When you have a media, obviously disposal is one of the key things in terms of, you know, a sustainable cycle. One of the things I mentioned, they'll get into next Thursday more, is that it can be desorbed. So we can, once our material is spent, you can desorb it easily, concentrate the waste stream into an amount that is disposable. And we have destruction techniques here to mineralize PFAS for kind of full cradle to grave treatment. Sheets, you just toss them out.
Fantastic. All right, awesome. Frank, thank you so much for joining us and offering that presentation. I'm really excited to introduce our next speaker, Chuck Meek, VP of SolvePFAS. Chuck?
Good morning. Thank you for having us. We're very excited to be joining this venue and this group. It's good to be talking with people of like mind. We're all pretty familiar with PFAS. We know that the EPA put PFAS on its CEC list as a contaminant of emerging concern, as well as an environmental emerging public health concern. And for many, some people don't think of it this way, but it's an emerging legal concern too. So every company that uses water in its manufacturing processes or just uses a lot of water has a new risk profile. And so the risk management is taken on a new sense of urgency within the boardrooms, et cetera.
Hey, Chuck, can you get a little closer to the mic? Sorry, you're fading in and out. Thanks.
I'm sorry.
That's okay. Thanks.
Hear me better now? Is it any better now? Did I mute?
Perfect.
So if you're on this call, you're probably familiar with the graphic, how PFAS contaminates our water, et cetera. The sources of PFAS in the nation's water supply are, they're extremely diverse. And it pushes on to get clarity on both the cause and effect of PFAS. Next slide, George. So the question for industry and really everyone who takes custody of and uses large volumes of water is, are you aware of the water quality coming in from the tap and going out down the drain? And if there's a delta between the two of the water coming in versus the water going out, do you know why? And so what we do is with our testing and tracking and measuring is we discern whether industrial processes are contributing to a problem or whether they inherited a problem when they bought the water to begin with. And so what they send down the drain really wasn't a function of what happened on their watch. So from an industrial standpoint, our clients take this data and they use it for their risk profiles and know what's coming down the road. If they're bringing in contaminated water and they're sending out contaminated water, then they are exculpated. If they are bringing in clean water and sending out dirty water or contaminated, they know they have a problem in their process that they need to fix. But until you know what's coming in and what's going out, you can't measure the delta. Next slide, George. So the point of this list is really to illustrate the sheer ubiquity of potential PFAS contamination. These are the the players in the PFAS culpability game that's coming down the pike. And I guess you could call it, it's the new list of usual suspects that people, meaning regulators, are going to be looking at in terms of where did this problem come from and where do we go to stem the tide and fix the problem or seek remuneration. Next, George. As the problem emerges, it shines a light on a growing problem, and that's lab capacity. We initially were working on water concerns at a Superfund site, and PFAS actually came in through the side door, and they said, "Can you help us with this?" And that's when we were introduced to the idea that there just is a dearth of lab capacity, fixed lab capacity, to measure and track PFAS contaminated, whether it's water, soil, air, whatever it is. There's just a finite number of labs that are capable of doing this. So adding infrastructure to the existing fixed lab network, it is capital intensive. It takes gas chromatographers and tandem mass spectrometer equipment. And it takes a real commitment on the labs because they do more than just PFAS. They also do heavy metals, they do all sorts of VOCs, et cetera. So there are very few labs for whom PFAS is the sole purpose for existence. And so they have a question to ask themselves, is it worth the capital infrastructure investment to ramp up capacity for PFAS when it's only one item on their menu of services? George, next please. So mobile PFAS labs will complement fixed labs for special situations. When transporting samples is logistically or it's time prohibitive, you have very remote sites. It's a bit like the treatment issue too. Do you pump and treat? Do you take the water to the plant to be remediated, or do you bring the remediation technology to the water? And because PFAS is so ubiquitous, it's in the groundwater, surface water, industrial wastewater, it's in our water supply, getting the water, even at the sample level, to the labs is logistically and time prohibitive for a lot of applications. So what we believe is that mobile gas chromatography and mass spectrometry will help in the allocation of scarce resources. We won't rely on the fixed labs and wait for all the water samples to come to them. We can figure out how to start doing some of the work in the field and reduce that time frame. Next slide, George. So mobility creates specific hurdles, though. The gas chromatography and mass spectrometry equipment is extremely sensitive. As Frank said, we're measuring the parts per trillion. That's an eyedropper in the Lincoln Memorial or Olympic-sized swimming pools, whatever the analogy is that you want to use. So do we focus on making lab equipment robust and fast calibrating to take it out into the field? Or do we look at the problem with fresh eyes, which is what we have chosen to do, and just seeing what's possible? What can we do with the right research players on it? So we've begun looking for what we call PFAS precursors and proxies. If you can't actually find parts per trillion in the single digit numbers out in the field with reliable, robust equipment, what can you look at that will give you a high indication that there is a PFAS problem here? Using total organofluorines or other proxies or precursors. And then the equipment that is used to identify those in the field doesn't need to be as robust. And so we are interested in finding ways to look for one echelon removed indicators of PFAS presence as opposed to the PFAS itself. And so this is what we say, what we mean when we say that mobility complements fixed labs. It doesn't really supplement them, doesn't replace them. We think it's an innovative way to allocate scarce resources so we can free up the fixed lab capacity for the known PFAS contaminants, but for all of the potential contaminated sites out there in these remote areas or within industry, within factories, if we can figure out a less expensive and more robust way to take the testing into the field, we think it will help allocate the scarce resources. Next slide, George. So I'm gonna mix metaphors a bit. At SolvePFAS, we're not trying to boil the ocean here. Success will come to us incrementally in a series of bunt singles. And so what we are looking for collaborations with others, looking for others who can sponsor research, who can fund contract research with the research partners. And this is where Kevin comes in with Halo. And it's a hand in glove fit. This is a live fire field application for what Kevin, what his reason for existence is to bring the problem to the problem solvers and act as that catalyst for that. And so, these special forces, they use terms down there at the bottom: adapt, improvise, and overcome. And that's what we're looking to do. I mean, PFAS is such a huge problem. We have to figure out different ways to address this in addition to the traditional. Thank you.
Great. Thanks so much for that, Chuck. We've got a bunch of questions, so I'm going to go ahead and take them in turn. James Reese, how fast in days can SolvePFAS turn around the testing results?
Single-digit days. So we have a lab in Chicago that's dedicated to PFAS. We have Agya Technologies equipment in there that's dedicated to PFAS. It's all calibrated. It's all ready to go. COVID has taken a bit of a hit on that. When the campus shut down, so did our lab. But that's just one of those adapt, improvise, and overcome situations that we'll have to deal with. So we bring the sample in, and it takes a certain finite amount of time for sample preparation. Then to run the sample, it's actually a very fast turnaround.
Mm-hmm. And can you have more than one lab? Like, would you need to have more than one testing site to do if at a certain scale? I'm assuming yes, but have you thought about that?
And what we're thinking of is the hub and spoke model, where we have a fixed lab as the hub, and then we either take remote testing capabilities outward on spokes and place those geographically around the hotspots around the country or around the world. But yes, it would take multiple of those. Otherwise, we just come up against the same fixed lab capacity problem that we all have now.
Yep. Great. We have a question about how volatile of PFAS for the GC measurement.
That has not been the issue that we have found. We stabilize the samples in the field, we ship them, we transport them. The bigger problem is the procedural and the possibility for cross-contamination. When you're looking at such minute contamination levels as parts per trillion, and things like Teflon tape on a plumbing fitting can contaminate a sample. That's why the equipment set up in the labs has to be plumbed very, very specifically with no Teflon tape, etc. So the cross-contamination is more of an issue for us than the volatility of the sample.
Great. And then I'm going to combine two questions about disposal of concentrated adsorbent sheets.
That's not really what we do. We don't have the remediation technology. That's not what we do. We are test, track, and measure. So we will take a very, very small amount of contaminated water and run that through a GC tandem MS machine. But we really don't have any waste to speak of other than just normal lab waste that goes with other.
Great. All right, thanks so much. Keep the questions coming, and Chuck, feel free to answer questions in the chat. I'm going to go ahead and keep us on track here and turn it over to introduce our next speaker, who's Brendan Ryan, CEO of Hydrus Technology Holdings. Brendan, take it away.
Hi there, guys. Elena, George, thanks a lot for the opportunity. I'm going to talk over the next 5 minutes about Hydrus Technology and our offering in treating the PFAS issue. If I could go to the next slide, please. So Hydrus was originally founded in Australia. In 2016, we moved our operations to Houston, Texas to address the US market. At the core of our technology is electrocoagulation. That technology has been around since the early 1900s, but we've done some patented upgrades to it. We've also developed a patent pending technique for encapsulating the PFAS material once we've cycled it up using EC. Electrocoagulation is, very good at removal of heavy metals, suspended solids, VOCs, and PFAS. We can also extract valuable minerals and materials from wastewater streams, and using the design upgrades that we've made to the technology itself, we have high efficiency rates. This enables us to provide services to both to landfill, mining, and oil and gas industries. We offer, our service model is sort of end-to-end water treatment service. So we bring capital equipment, operations to the site to provide the treatment, and our customers typically pay a tolling fee for treated water. Those pictures in that slide represent the modular system, which is containerized and mobile. The system is operated by controlled by a PLC, and the picture on the right there represents sort of a typical landfill setup with full facilities, including tankage and other ancillary treatment equipment that we would typically deploy. Where we've seen the advantage of electrocoagulation in addressing PFAS, it really creates conditions, that enable us to basically cycle up the PFAS material. If I could go to the next slide, please. In the center there's sort of an illustration of how electrocoagulation works. Primarily, it's the use of electricity and sacrificial anodes. We have a metal anode and cathode that are placed within the reactor. With the application of electricity, we generate hydrogen gas and hydroxyl groups. The electron flow basically destabilizes the charges on the suspended matter and liquids within that reactor. And then these larger groups of suspended matter coagulate, and that enables us to effectively separate them. The application of of EC is basically understanding, the chemistry that occurs within it and the target analytes themselves. So two things are really happening, where we create sort of basic conditions where the PFAS is presented in its ionized form. Therefore, it's most likely to combine with other materials that enable us to basically separate it and partition it. And then secondly, we're creating gas bubbles within the reactor that enable us to, again, separate the PFAS. If we go to the next slide. So when we looked at the problem here, we basically took a two-step approach. The first was sequestering the PFAS material itself, and that's a function of the EC reactor. And then looking at the long-term disposition of the PFAS. And so we went the route of encapsulation versus destruction. Again, the rationale for using EC, PFAS materials really don't like to be surrounded by anything. They don't like water, they don't like fats, and so the EC reactor creates this environment that enables us to effectively cycle them up into a liquid gas interface and then stabilize in a foam. The other thing about EC is it's very good at targeting small concentrations of material and materials that are not very or sparingly soluble in water. So this fits in the wheelhouse of EC itself. And then the other challenge that we found was some of the destructive techniques can be problematic in that they aren't as effective oftentimes, and therefore the fact of being able to cycle them up and isolate them and contain them is a commercially viable option. The table to the left there shows the impact that we had on these 6 analytes that were the longer chain carbon compounds are more common targets for us as we're treating leachate, and particularly on account of providing the greatest health risks. But you can see that the effect of the treatment itself cycled them up to greater than 90% in all cases, and in certain cases up to 99%. So this gives us, a powerful tool for cycling up the PFAS. And if we could go to the next slide, which sort of describes step 2, and this is an encapsulation technique. So basically here we are taking the concentrate foam and creating a modified concrete material that has structural stability. So this can actually be used for additional purposes in construction itself, or converted into a form that can be stored back in the landfill. The testing that we did here, the second column there in that table shows the PFAS concentrate in the foam material, and then once we stabilize it into this modified concrete form, we carried out a modified T-clip test to determine its leaching properties, and those results are shown in column 3 there. So the material actually passed the T-clip test, and therefore enables us to place it back into the landfill or reuse it for additional purposes. We go to the next slide. So once we have, so the market that we're basically targeting at this point is the landfill sector. There's more than 2,400 landfills in the United States, producing 7.2 billion gallons of leachate a year. I mean, the benefit of a landfill is we get to consolidate our waste in it. The approach that we're taking is treat the PFAS at the source and keep it at its source by encapsulating it. A lot of people obviously don't want to live or have a landfill in their backyard, but it is an effective method for us to treat leachate, given that, this is a source, because all of these materials are effectively making their way back into the landfill. So with that, I'll stop and answer any questions.
Great, thanks for that. I'm sorting through, there's a lot of chat traffic here. It looks like, let's see. What happens to the hydrogen gas, and how is that explosion hazard managed? I'm combining 2 questions.
Yes, we have blowers in the facility, and so we keep it below its ignition level.
Great. Let's see. Do we have, let's see, any more questions in the chat about this? I think that was the only one. Lots more chatter for Cyclopure. If not, to keep us on time, we have one final presentation.
Brendan, thank you so much for being with us today and sharing your presentation. And our next presentation will be Brian Chaplin, who is an associate professor at UIC, but also co-founder of the Zyvant Research Innovations.
Great.
Okay, thank you very much, Lena and George and everyone else at Current for including me in this workshop. And so thank you very much for the introduction. I'm happy to be here today and share with you a new technology that we have developed at UIC. So we have patented what we call a reactive electrochemical membrane technology, and we're utilizing this for multifaceted electrochemical water treatment. So just briefly, I'll overview this technology. This technology is a chemical-free process, and so we utilize an electrical current to degrade contaminants. We also have utilized this for controlling membrane fouling and achieving disinfection of pathogens in water treatment. And so really the goal here with this technology is to replace several water treatment unit operations with this single REM technology. And so just, I'll go over the technology briefly. So the technology is basically a ceramic membrane, but we have developed a conductive material. And so that allows it to have all the features that you would have for a ceramic microfiltration membrane, but we also can impart reactivity. So we have developed this for various applications. I'll focus primarily on PFAS today. And so we have a prototype system, which I'm showing at the top of this slide, which can treat about 50 to 100 liters per day. So right now we're operating at the lab scale. I'm hoping to scale this up. And we've tested a variety of waste streams. Our current focus is on PFAS mineralization. And basically what we can do is we can apply an electrical current and we can oxidize PFAS to its mineral products. So instead of just sequestering the waste, which can have problems, we can destroy it completely and go to products of, for example, fluoride and CO2. And so we're currently testing the REM for destruction of PFAS in contaminated groundwater, as well as municipal wastewater side streams, landfill leachates, and industrial effluents. And so in having this destructive method for PFAS allows us to remove it from the environment and take it out of the water cycle. A few other applications that we're looking at, we're also looking at oxidation of a variety of other micropollutants, reduction of contaminants as well, such as nitrate, fouling control, so controlling fouling that would occur in membrane systems, and as I said before, disinfection of pathogens in water. So next slide, please. Okay, so as we all know, there's an urgent need for both a cost-effective and destructive treatment strategy for PFAS. And this really has application, as you've already seen, in various different scenarios. So the PFAS, as we know, are toxic at low levels. The EPA has set health advisory levels at less than 70 nanograms per liter, but various states are really taking the lead in this and have set much, much lower levels. And I've heard people saying, we want to get down to single nanogram per liter levels of these PFAS. And so this is a really big challenge because there are hundreds upon hundreds of different PFAS compounds. Not all of them have been identified. And in addition to that, the PFAS are very resistant to traditional treatment processes. So there are very few treatment technologies that are able to degrade PFAS. And this includes things like typical advanced oxidation processes, which have been kind of the go-to technology for very recalcitrant compounds. So our technology, this REM technology, we can achieve complete PFAS destruction, and we can do this at low energy costs and without chemical addition. So we're basically piggybacking on a membrane platform. And so with that, we are looking at different strategies in terms of once through operation. So for example, passing the contaminated solutions once through the membranes at fluxes that are equivalent to those that we would use on a membrane operation, and achieving, in some cases, complete destruction of these compounds. Next slide, please.
Hey, Brian, before we advance, sorry, there were several technical questions in the chat that I think relate to this that I just wondered if we could go deeper on while we're on the slide.
Yeah, sure.
Yeah, so pore size, what's the pore size?
Yeah, so this is a microfiltration membrane. So we're looking at pore sizes of around 0.1 microns and a little bit bigger. So anywhere 0.1 to 0.2 microns.
Great. And then did you say what's the minimum size of suspended particulates that can be removed this way? Minimum size with electrocoagulation? I don't know if you...
This is not electrocoagulation.
Oh, sorry. Sorry, wrong.
So microfiltration membranes, if we're looking at, for example, 0.1 microns,
yep,
and they're going to remove anything bigger than 0.1 microns.
Great. And then
and so we can tailor the pore size, different sizes. And so we go from being maybe micron size, and we've gone down to nanometer size as well. Yeah. But we find that the size that works best for the most applications when we're more focused on contaminant removal are the micron size, because we have less problems with clogging. And so the pretreatment, which is probably a question, I haven't looked at the chat, but that's typically always a question. And so you can think about the pretreatment would be similar to what you would do for a microfiltration membrane. So there's some particle removal lots of times that's needed, and that's usually something like a 1 micron filter. And then we have to operate this in terms of doing back flushes sometimes as well to remove particle fouling that occurs over time.
Yep. And I don't know if you're going to get to this. Is there an energy? What's the energy requirement?
I have one slide that
Okay.
that shows that. Yeah.
Okay, I'll let you go ahead. There's just we've got a very active chat going, so you may.
No problem. Yeah.
Great.
So the energy is right here. Okay. And so this is one application that we're showing. This is for groundwater remediation. As I mentioned, we are currently looking at lots of different waste streams. And so with this particular groundwater, this had PFAS contamination in the parts per billion levels, so micrograms per liter levels. And there were 6 different PFAS compounds, including long chains as well as short chains. And so we treated the water with our REM technology. We were able to get total PFAS destruction of greater than 99%. And individual PFAS concentrations at the end of the treatment were all less than 61 nanograms per liter. And so we calculate the energy, and this is for the energy to run the reactors, so power the electrodes. And so we're reporting this in what's known as EEO, or per log removal. And so this treatment provided an energy of 2.9 kilowatt hours per cubic meter of water, and this is normalized per log removal. So for example, we have about 2 log removal here, so the total electricity used to power the REM is about double what I'm showing here. But it's good to normalize per log removal, so it can be easily compared to other technologies. And then the cost of pumping is not included in here, but that's typically very low and on the order of only about 5 cents, or excuse me, 5 kilowatt hours per cubic meter. So next slide, please. And so, yeah, that's it. It's a very brief presentation. So, you know, what we're looking for here is for more collaborations to validate this technology. And so the target customers are basically everyone, because PFAS is, you know, we've found it everywhere: drinking water, wastewater, groundwater, solid waste in terms of landfill leachates. And we're also specifically focused on trying to develop point of use treatment. And so for impacted communities that may be off the grid and have contaminated groundwater. And so this technology lends itself very nicely to point of use treatment because it's very simple. We just need an electrical source, no chemical addition, and the maintenance is relatively low. So next slide, please. Okay, so there I am again, much younger. And here's my contact information, so you can email me at UIC. This is the technology is currently held at UIC. I also have a consulting company for general water treatment consulting, and you can reach me at either email, and there's a website to Zyvant Research Innovations. So that's all, and I'll be happy to answer any questions.
Great, thanks so much, Brian. Yeah, there's a ton of questions. I think everyone's going to end up, you may take some of these in email. You can also respond on the chat while I'm doing the wrap up. We're getting close to time here, but there were multiple questions about destruction mechanism and the requirement of high concentrations, like how many parts per million. So can you maybe just say a little bit more about destruction mechanism process than you elaborated on already?
Oh, sure.
Difference between destruction and sequestration as well. That'd be great.
Yeah, so this is completely destructive method, and so yeah, the mechanism for destruction is I don't know how detailed I want to get into this, but it's a direct electron transfer. So basically, the PFAS molecule needs to get close to the surface. It doesn't need to absorb, but it has to get very close to the surface. And then basically, if you get the potential high enough at the REM surface, then the electron will jump from the PFAS molecule to the electrode, and that creates a radical, and then there's a series of reactions that follow that ultimately leads to complete mineralization. And so basically there are intermediates in this process as well, so this is why this is very challenging. And it's basically what you see are shorter chain compounds form from the longer chain, and eventually you know, we can degrade those all the way to the mineralization products. The short chain ones seem to be a little more difficult to oxidize than the longer chain ones. And so that's going to be the real challenge in treatment, is that, you know, the remediation designs have to be geared towards complete mineralization and not just removal of the parent compound. You know, a lot of us have heard of PFAS, PFOA,
Yeah.
Once we degrade those, shorter chain ones can form. And so we really have to be mindful of a complete characterization of the water to make sure that we're removing all the compounds that could be toxic.
Yeah, great. Yeah, and I guess you may have not know this yet, but I know this came up earlier, a question about just the economics of deployment and how much concentration you need to get to make this economically feasible to deploy at different scales, or maybe that's something you hope to learn in future.
Yeah, I think that's something that we're hoping to learn over the the next year or so. We have lots of projects, lots of funded research on these different streams, and really the next stage for us is scaling up to answer those questions. The cost, material cost, is relatively low, so we're not using any precious metal catalysts in this system. This is all titanium-based technology, so it's very cheap, so we hope that the economics look very favorable. The electrodes have a very long lifetime as well, and so we won't be replacing them very frequently. But yeah, I mean, to give specifics, I would just be kind of guessing at this point.
Yep, great. Well, just in the spirit of keeping us on time, I'm going to go ahead and leave the chat open for Brian to respond to other individual questions as he's able to. We'll leave it open a few minutes after we go ahead and close the session. But just in closing, I want to say first, it's great to have Brian and UIC represented, as Current is really invested in solving big problems in water globally, but we're also deeply invested in building the strength of our local innovation community here in Chicago and Illinois. So it's great to have UIC. I also neglected to mention up front, but this Innovators Workshop and this topic of PFAS is actually a really critical component of a large multinational consortium that it's a binational project with the US and Israel that Northwestern's actually leading. And so many of the partners here are part of that consortium, and it really represents this incredible binational commitment to understanding this issue, and in particular to sort of building the connections between the universities, utilities, industries, and startups that are all trying to solve this critical problem. So we're excited to sort of have this Innovator Showcase be part of a kickoff for that co-work consortium, and Current is really privileged to be a partner to that project, and so happy that Northwestern has taken the lead. How you can stay engaged with us: there's a QR code on your screen. You can scan that, and that'll take you straight to our events page, which will list other future Innovators Forums like this one on other topics, as well as large events. Like we have a really exciting virtual screening of the new documentary, Brave Blue World, coming up right here this week. We're really excited about that. And we are always interested in responding to your ideas for events that would be useful, topical, and helping us advance our goal of growing Chicago's water innovation community. So please reach out to George Burgandy, my colleague who masterminds all of our events. His email is right on the screen if you want to collaborate on a future event. George, is there one next slide, I believe? Great. So right on screen, you can also see direct contact links for our partners, ChicagoNEXT and Kevin at Halo. And I do want to tease, Kevin mentioned we'd say a little bit more about the Halo partnership. Halo, like Current, exists to really strengthen the supply and demand sides of water technology innovation. So we are really excited to be looking for 3 flagship industry partners to help us launch the water sector of Halo's offering on research and R&D connections. Current and Halo are partnering on that, so we'll be offering a blended suite of membership benefits. If your industry is interested in potentially becoming one of those 3 flagship partners that we'll announce later this year, you can get in touch with me or you can get in touch with Kevin. Both of us will be working sort of hand in glove to shape up that partnership, but we're really excited on the interest we've gotten so far. And this topic is one of many that I know will be using this platform to accelerate. So we are thrilled that everyone could join us today. This is the biggest turnout we've ever had for one of these. And of course, you'll be able to share this video via our YouTube channel for anyone that wasn't able to attend and might want to tune in. So I just want to, on behalf of all our partners, thank everybody here, particularly thank our innovators who are working so hard to solve these pressing challenges. And we'll see you next time on the next edition of the Innovator Showcase. Thanks, everybody.